The ground beneath Batangas and southern Luzon shook again on August 20th, 2025, when a magnitude 4.8 earthquake struck just 2.2 kilometers north of Sinisian, Batangas. Its focus lay deep 72 kilometers 45 miles below the surface. That tremor came only 2 days after a magnitude 4.5 quake beneath Manila on August 17th. Originating at a depth of 166 kilometers 103 miles, and another on August 16th, registering magnitude 4.9 near Hukay, Batangas, some 164 kilometers 102 miles down. All three quakes clustered within the Philippine subduction system, where the Philippine Sea Plate grinds beneath Luzon along the Manila and Philippine Trenches. Their depths, far below the brittle crust, mark them as part of slab deformation, where oceanic lithosphere bends, fractures, and undergoes mineral transformations under crushing pressures. Individually, such deep focus quakes are rarely destructive, releasing their energy far beneath populated areas. They seldom produce tsunamis and usually pass as scientific curiosities. Yet their timing and concentration near one of the archipelago's most dangerous volcanoes, Taal, have raised scientific eyebrows. In tectonic regions where magmatic arcs form, sequences of deep earthquakes can sometimes herald changes in the stress field that reverberate upward. In rare cases, such changes can influence the pathways of magma migration. PHIVOLACIS, the Philippine Institute of Volcanology and Seismology, quickly assured the public that Taal remains at alert level 1. That level denotes abnormal activity but no imminent eruption. Still, officials reiterated that Volcano Island, the small landmass within Taal Lake that hosts the active vents, remains a permanent danger zone. Residents were reminded that no settlement is permitted there, a rule born of bitter experience. Despite the measured language, the clustering of deep quakes beneath the Luzon Arc has not gone unnoticed. Scientists in Manila, Tokyo and beyond are debating whether the stresses could link to Taal's deeper magma reservoirs. To understand why such tremors stir anxiety, one must consider the geologic framework of the Philippines. The country sits astride one of Earth's most intricate tectonic knots. To the west, the Manila Trench swallows the South China Sea seafloor beneath Luzon. To the east, the Philippine Trench does the same with older portions of the Pacific seafloor. These converging subduction systems forge the Luzon volcanic arc, a string of active volcanoes stretching hundreds of kilometers. Subduction zones are magmatic foundries. As oceanic plates descend, their hydrated minerals release fluids that lower the melting point of the overlying mantle wedge. This generates magma that rises, stalls or accumulates in reservoirs beneath volcanic centers. Over tens of thousands of years, these processes carve the silhouettes of Mayon, Pinatubo, Bulusan, Banahaw, and at the center of southern Luzon, Taal. Taal volcano presents an almost deceptive calm. At first glance, it is a circular lake some 24 kilometers, 15 miles, across, ringed by the slopes of an older volcanic edifice. In the middle lies Volcano Island, only a few kilometers wide, whose central crater still smoulders with fumaroles. Yet this picturesque scene hides a violent prehistory. The lake itself is a flooded caldera, a depression formed when a massive volume of magma erupted and the overlying ground collapsed. Geological surveys and tephra layers preserved in surrounding soils suggest that Taal's ancient caldera-forming events may have exceeded anything witnessed in historic times. The prehistoric complexity of Taal's caldera is poorly understood compared with Pinatubo, but clues suggest multiple collapse events rather than a single catastrophe. Some models propose that Taal's lake basin formed through overlapping calderas, each carved by large eruptions separated by thousands of years. The stratigraphy surrounding the region reveals thick ignimbrites, welded tuffs from pyroclastic density currents, indicating that eruptions far larger than those of the last 500 years once occurred. Radiometric dating of deposits points to at least one major eruption in the Holocene that may have approached VEI 5 to 6, though the evidence is fragmentary. If true, this would mark Taal as a caldera system, with more potential than its diminutive island suggests. In historic times, Taal's eruptions have been frequent but moderate in size, often between VII-2 and VI-4. In 1754, Taal endured its longest eruption, lasting almost 200 days, devastating towns along its shores with heavy ash, scoria and pyroclastic surges. The 1911 eruption was shorter but more lethal, killing over 1,300 people as base surges swept across the lake with little warning. Survivors described how the blast was preceded by almost no precursory activity, an unsettling reminder of how suddenly Taal can awaken. In 1965, phreatomagmatic explosions created towering columns of ash as lake water interacted explosively with rising magma. That eruption was rated VEI-4, comparable in explosive energy to Mount St. Helens in 1980. The most recent significant activity occurred in January 2020. A relatively modest phreatic eruption sent ash plumes up to 14 kilometers, 9 miles high. Despite being rated only VII-2, the eruption displaced nearly 500,000 people and caused widespread ashfall in Metro Manila, 60 kilometers, 37 miles away. Flights were grounded, schools closed, and agriculture was damaged. The disparity between its modest magnitude and its enormous impact illustrated a sobering truth. Taal's hazard is amplified not only by its volcanic behavior but also by its location amid one of the most densely populated corridors in the Philippines. In contrast stands Mount Pinatubo, 120 kilometers, 75 miles to the north, whose 1991 eruption remains the largest of the 20th century. That VEI-6 event expelled more than 5 cubic kilometers, 1.2 cubic miles of magma, lofted ash 35 kilometers, 22 miles, into the stratosphere, and cooled global temperatures by about 0.5 degrees Celsius for several years. The scale dwarfed Taal's historic output. Yet volcanologists caution against assuming that Taal cannot, under rare conditions, achieve similar violence. The critical question is whether Taal's magmatic plumbing system can accumulate the volumes required for a VII-6 eruption. Pinatubo is a large stratovolcano, its magma chambers capable of storing enormous quantities of silicic magma. Taal, by contrast, is smaller, with frequent eruptions that tend to release pressure before catastrophic buildup. Still, caldera systems are inherently deceptive. Their fragmented structure, ring faults, and deep connections can conceal vast reservoirs. Some geophysical models suggest that Taal's magma source is replenished not only by shallow crustal melts, but also by basaltic inputs from deep mantle wedge processes. If such basaltic injections mix with more evolved, silica-rich magma, they can trigger runaway explosivity. A VEI-6 eruption at Taal would be catastrophic. Ash columns would likely exceed 30 kilometers, 18 miles, injecting aerosols into the stratosphere. Fallout would blanket much of southern Luzon, collapsing roofs in Cavite, Batangas, Laguna, and potentially Manila itself. Pyroclastic surges could sweep across Taal Lake in minutes, annihilating lakeshore towns. Secondary effects would ripple outward. Lahars down river systems, agriculture smothered, air travel paralyzed. With Manila's population exceeding 13 million, the humanitarian toll could eclipse Pinatubo, not in scale of eruption, but in scale of human impact. This prospect, though speculative, is not dismissed. Geological history shows that Taal has produced complex caldera collapses and widespread ignimbrite deposits. The timing of its last truly major eruption remains debated, but thousands of years may have passed since. Such a timescale leaves open the possibility that pressure has again been building. The recent sequence of deep earthquakes may or may not connect to that system, but they remind scientists that tectonic stress beneath Luzon remains active and unpredictable. The challenge lies in monitoring a volcano of such complexity. Taal is not a simple cone with a single conduit. It is a nested system of vents, dikes, faults and shallow lakes interacting in ways that defy easy modelling. Eruptions can emerge suddenly from new fissures. Water-magma interaction often dominates, creating violent surges even when the magma volume is small. This makes forecasting difficult. Seismic swarms, ground deformation and gas emissions can rise and fall without culminating in a major eruption. Yet volcanologists know that under rare but possible alignments of pressure, composition and external water supply, the system could unleash far more than it has in recent centuries. For now, Taal rests at alert level 1, quietly steaming in its crater. Tourists admire the lake from ridges in Tagaytay, unaware that they stand on the rim of an ancient caldera scar. But beneath the placid waters, magma accumulates, gases exsolve, and stresses shift. Processes that, given the right trigger, could cascade into a chain of events larger than anything in living memory. If history has taught anything about volcanoes, it is that their true capacities are often underestimated. The geological record holds reminders that small or moderate-looking systems can, under the right pressures, unleash devastation on a scale out of proportion to their apparent size. For Taal, this possibility is especially troubling. Unlike remote caldera systems hidden in wilderness, Taal is situated in a heavily populated corridor, surrounded by towns, agriculture, and within striking distance of Metro Manila. If the volcano were ever to reach VEI 6 magnitude, the consequences would be measured not only in cubic kilometers of magma, but in human lives disrupted by the millions. Understanding how such an event could happen requires looking into the mechanics of caldera eruptions. A VEI 6 eruption typically involves the evacuation of more than 10 cubic kilometers, 2.4 cubic miles of magma. This requires a large, evolved magma chamber, rich in volatiles such as water vapor, carbon dioxide and sulfur dioxide. Over time, basaltic magma intrudes from below, adding heat and fresh material to the chamber. When mixing occurs, it destabilizes the stratified reservoir. Pressure builds as gases exsolve, and once the tensile strength of the overlying rock is exceeded, the chamber roof fractures. What follows is not a simple explosion, but a sequence. Eruption columns shoot skyward, pyroclastic flows sweep outward, and finally the chamber roof collapses, creating or expanding a caldera. In Taal's case, the existence of Taal Lake itself is proof that such caldera-forming processes occurred in the past. The large basin is unlikely to have formed from small VEI 3 or VEI 4 eruptions. Only repeated or very large events could excavate such a depression. This suggests that beneath the present-day volcano island lies a complex, possibly multi-tiered magma storage system. Some geophysical interpretations propose that a shallow reservoir sits at 5 to 7 kilometers, 3 to 4 miles depth, with a deeper basalt-fed reservoir at 15 to 20 kilometers, 9 to 12 miles. These reservoirs may periodically interact. If the deeper system delivers a sudden injection of basaltic magma into the shallower chamber, the resulting mixing could provide the trigger for a large eruption. Such a mechanism has been proposed for other caldera systems, including Santorini in Greece and Taupo in New Zealand, both of which have produced VEI 6 to 7 events in the Holocene. For Taal, while direct evidence remains scarce, the chemistry of past eruptions indicates a wide range of magma compositions from basaltic to dacitic. This diversity implies that magma evolution and mixing are active processes in the system. A sudden destabilization could, in theory, set the stage for a climactic eruption not seen in modern history. Were Taal to erupt at VEI 6 scale, the sequence of hazards would unfold rapidly. An initial eruption column would likely rise to 30 to 35 kilometers, 18 to 22 miles, injecting fine ash and aerosols into the stratosphere. Ashfall would extend well beyond southern Luzon, potentially reaching as far as central Luzon and the Visayas. Roof collapses would threaten communities within 100 kilometers, 62 miles. Manila's water reservoirs, including Angat and La Mesa, could become contaminated with volcanic ash, complicating water supply for millions. Closer to the caldera, pyroclastic flows would surge across the lake. These base surges, travelling at hundreds of kilometers per hour, could obliterate lakeshore towns within minutes. The permanent danger zone around Volcano Island would be wholly engulfed. Tagaytay Ridge, with its popular hotels and residential communities, would likely suffer heavy ashfall and possible pyroclastic impacts on its lower slopes. Infrastructure, highways, bridges and power lines would buckle under the weight of ash and lahars. In the months following, heavy rains would remobilize ash into deadly mud flows, similar to those that buried villages in Pampanga after Pinatubo's eruption. The regional and even global impacts would not be trivial. Pinatubo's 1991 eruption released about 20 million tons of sulfur dioxide, cooling the planet by 0.5 degrees Celsius. If Taal approached VI6, a comparable sulfur release could be expected. The precise climate effect would depend on how high the eruption columns rose and how efficiently sulfur dioxide was converted to sulfate aerosols. Still, even a temporary global cooling of 0.3 to 0.5 degrees Celsius would disrupt agriculture across the tropics, adding an international dimension to a national disaster. This speculative scenario raises pressing questions about preparedness. Monitoring Taal is notoriously challenging. Its eruptions are often phreatomagmatic, driven by water-magma interaction, making them sudden and explosive. The January 2020 eruption occurred with less than 24 hours of escalating seismicity, leaving little time for comprehensive evacuation. Pinatubo in 1991 gave several months of warning, but even then scientists debated whether a climactic eruption was imminent until the last moment. Taal's complex hydrothermal system and multiple vents add further ambiguity to seismic and gas signals. Phivolcs maintains a dense network of instruments, seismometers to detect microquakes, GPS stations to measure ground deformation, spectrometers to track sulfur dioxide emissions, and satellites to monitor thermal anomalies. Yet the greatest challenge remains interpretation. Magma may intrude without erupting, gases may fluctuate without leading to explosions, and shallow phreatic eruptions may occur without involving magma at all. The task of distinguishing harmless restlessness from a brewing catastrophe is a heavy burden. In terms of disaster readiness, the Philippines has learned from Pinatubo. Evacuation centres, communication systems and international collaborations are far more robust today. Still, the scale of displacement required by a VEI-6 eruption would test even the best prepared plans. An estimated 1.2 million people live within 30 kilometres, 19 miles of Taal, many in lakeshore communities with limited evacuation routes. Roads leading out of Batangas frequently bottleneck even under ordinary traffic, raising fears of gridlock during an emergency. Manila, though 60 kilometres away, would not escape. Heavy ashfall could ground flights for weeks, shut down businesses, and force mass closures of schools and offices. Comparisons with Pinatubo provide perspective. In 1991, timely warnings and evacuations saved tens of thousands of lives. Yet even with success, the eruption displaced 200,000 people and reshaped central Luzon for decades. A VEI-6 eruption at Taal would threaten a population at least 5 times larger. The humanitarian, economic and political consequences would be severe. Global markets would register the shock of disrupted trade, grounded flights and regional instability. For now, however, the system remains quiet. The recent deep earthquakes beneath Batangas and Manila may be no more than tectonic readjustments, disconnected from Taal's magma reservoirs. Phivolcs stresses that no abnormal uplift or sustained swarms of shallow quakes have been recorded. Sulfur dioxide emissions remain elevated but not extreme. In short, there is no evidence that a large eruption is imminent, yet volcanologists emphasize vigilance. Pinatubo reminded the world that large eruptions can sometimes unfold on the scale of weeks. To assume Taal incapable of the same would be a dangerous complacency. The paradox of Taal is that it is both familiar and enigmatic. Millions have gazed across its lake, dined along Tagaytay's ridges, or ferried across to Volcano Island, yet beneath its tranquil surface lies a restless and poorly understood system, one capable of small steam bursts one year and perhaps something far larger in the geologic blink of an eye. The August 2025 tremors serve as a reminder that the Philippine arc is not static. It is a living, grinding, magmatic machine. While the probability of a VEI-6 eruption at Taal may be low in any given decade, the stakes of such an event demand continuous attention. The lesson of Pinatubo was clear. Science, vigilance and public communication can save lives. The lesson of Taal is more unsettling. Even small volcanoes can wield disproportionate power, especially when surrounded by dense populations. As scientists keep their instruments trained on southern Luzon, the public must remain prepared, not panicked, but ready. Because when it comes to volcanoes, the past is never a perfect predictor, and the future is always capable of surprise. And as the world watches the placid waters of Taal Lake shimmering under the Philippine sun, one question endures. Will the next great eruption be a modest outburst or a cataclysm on the scale of Pinatubo or worse? Only time and the restless earth will decide. If you found this video insightful, don't forget to like, share and subscribe so more people can stay informed about the science, risks and realities of the world's most dangerous volcanoes.